Thank you for inviting me to talk to you. Today, I'll discuss a perspective on teaching and learning, which can provide insights when learning goes wrong, and can be used by the teacher who sets out to be a learning doctor by diagnosing and debugging learning impediments. I am considering that teaching learning is a system, and so when the process breaks down, we can look for the bugs in the system. I'm going to start the talk by setting out the general idea. Hopefully, most of the principles will be familiar to you, as they're well established, and I'm simply shaping them into a particular perspective that may not be so familiar. So I trust this will be as if I'm introducing you to a structural formula for a compound you're not familiar with, but where you will recognise all the components. Apologies to those of you who do recognise this as oxytocin, but even if you've never seen this structural formula before, most of you will appreciate it's just built up from very familiar elements. Once I've organised these familiar ideas to explain the learning doctor approach and its typology of learning impediments, I'll discuss some examples of where teaching learning can go wrong and relate these to the model. Time only allows a modest range of examples, but I think these should be sufficient to illustrate the core idea. I hope this will persuade many of you that this model is useful enough to add to your mental toolbox of pedagogic perspectives, useful to apply in teaching or in analysing learner thinking. However, it is important to first set out the range of application of this idea. There are many reasons why students do not always learn what we would like them to. Students may be absent from class, but this perspective will not help there. Or a student may be present, but for various reasons too tired or too hungry or thirsty, or too scared or sad to be able to effectively engage in learning. In these situations, then, the causes of that state need to be addressed, and these may often be outside the direct control of the teacher. Indeed, sometimes, as in bereavement, there may be nothing a teacher can do in regards to the student's learning, but allow the learner time. Again, the approach to be discussed today cannot help in these situations. Or there may be an attitudinal issue that relates to the breakdown in the relationship between the teacher and the student, such that the student disengages with learning in that class. Or some prior experiences which have led to the student concluding that they do not understand this subject and will never be any good at it. Here, the teacher may well be able to address the issues, at least given time, but again, the model I'm discussing today will not be the tool to employ. Finally, perhaps communication is not effective for some practical reason. Perhaps because the student is too far away from the teacher to see clearly, or has an obstructed view of the board or screen, or has forgotten or lost eyeglasses, or the environment is too noisy to allow the student to hear clearly, or the board is obscured by reflected sunlight, or whatever. In which case, this is the problem that first needs to be addressed. These are all issues that prevent the teaching learning system being engaged. My concern today is more with what often happens when the system is engaged, but does not produce the learning hoped for. Normally, we are concerned with class teaching, in a classroom or lecture hall, with 20, 40, maybe 100 learners. That complicates teaching immensely, but for the purposes of our analysis today, we will consider the teaching learning system as involving a teacher and one learner, so the teacher may be part of many such systems at once. The key elements are the teacher and a learner who are able to clearly communicate information to each other. So, I am talking about the teacher-learner system, but the actual teaching-learning context facing the teacher is a manifold of these unitary systems. The system I am discussing is based on assuming there is a teacher who wishes to teach some curriculum material that has been prepared for the class, and a learner who is present, willing, and in a fit state to learn, who is paying attention in class, and where there is a good communication channel, which will normally mean that the learner and teacher can see and hear each other clearly. I'm sure you will agree, even when this system exists, we cannot be confident the learner will always understand what is being taught in the manner intended. Sometimes it happens, but sometimes not. So there are often bugs in this system. I should also point out that even when teaching does lead to the intended understanding of curriculum material, that does not mean the learner will still understand it in the same way in the next lesson, let alone by the time they may be formally tested in an examination. There are strategies and tactics teachers can employ to reinforce initially fragile learning so it becomes robust. But they are only relevant once the student initially understands the new material. So today, my focus is on that immediate aspect of teaching and what can go wrong at that stage. Before proceeding, I'm going to set out how I use some key terms. I'm talking of conceptual learning rather than, for example, teaching manipulative skills, such as using a barrette or focusing a microscope. My notion of concept is quite inclusive. By concept, I mean any kind of mental category. Let me explain that. If a student has some basis on which to suggest whether something can be categorized in some way, then I consider that to be having a concept. So if they could respond meaningfully to a question such as, is this or that an atom, an example of oxidation, a food web, a test tube, a resistor, a tangent, or whatever, then they have some concept associated with that label. All concepts are in a sense abstractions, the abstraction of a commonality from across different examples. But these concepts met in school science can be at very different levels of abstraction. There are different types of concepts. Some concepts refer to things, or types of things. Some refer to processes that occur, and some to the qualities we use to describe. That may sound quite straightforward, but of course in science, the things, events and properties that we discuss may be invisible or even imaginary. That is, some of these concepts may seem very abstract to learners. Some concepts do not refer to any direct reference, not even to a very minute referent like an electron, or an imaginary one like an ideal gas, but only to relationships between other concepts. So this category includes all our principles and laws and theories and so forth. Teachers often need to use similes and analogies and models and representations to help make such abstractions of abstractions seem more concrete for learners. I assume that a person has a conceptual structure, which we can imagine as an extensive web or net with concepts as nodes, and the links being the perceived connections between nodes. These can be represented by propositions, such as, for example, mammals are vertebrates, or metals are electrical conductors. Although a person cannot always verbalise a connection they are at some level aware of. Each of these aspects of a person's concept might be labelled a conception. So the canonical conception that all metals conduct electricity, and the alternative conception that all metals are magnetic, might both be part of a learner's concept of metals. We might suggest the content of a concept is the sum of all those propositions, all those conceptions, that is, all those connections embedding the concept in the wider conceptual structure. A person's concept may be more or less canonical according to how well the component conceptions match the scientific account. We can model the conceptual structure in a simplified way as a kind of concept map. It's worth noting that there is a kind of conceptual inductive effect, named by analogy with the inductive effect in large molecules, in that the total content of a concept depends on its associations with other linked concepts, but the meaning of these concepts is also dependent on their other associations with further concepts that are only indirectly linked with our original concept. If that should seem a little obscure, think about the conception that vitamin C is an acid. That is a perfectly canonical conception. However, if a learner who held this appropriate conception also had the conception that all acids were harmful and would be dangerous to touch or ingest, then that will be an unhelpful alternative conception. Because the learner incorrectly sees all acids as harmful, this colours their view of ascorbic acid, vitamin C, as correctly knowing that vitamin C is an acid will lead to the incorrect inference, the logical deduction, that vitamin C is a hazardous substance which should not be ingested. That is what I mean by the conceptual inductive effect. The content of a person's concept is influenced by the other concepts indirectly associated with it. By understanding, I mean making sense of something. A student may have some understanding of, say, electrical fields, but this understanding may be neither extensive nor canonical. Usually in teaching, we're intending to develop a learner's understanding, both in terms of deepening understanding and in terms of increasing the match to the canonical account. Deepening understanding may refer to better appreciating the correct range of application of a principle, or being able to correctly apply it more widely, but could also mean embedding a concept more thoroughly in a web of other related concepts. As Albert Einstein commented on a number of occasions, science seeks to encompass the greatest range of phenomena under the least number of basic principles. And I think increasing learners' levels of conceptual integration is a key aim of an authentic science education. The concepts met in the curriculum may be very complex and sophisticated and nuanced. So in teaching, there is often a simplified, more limited target version of the canonical concepts set out, a curriculum model of the scientific idea. In presenting these ideas, teachers sometimes use teaching models which may simplify things further if the teacher judges this is needed for students to make good sense of the topic. Ideally, after the teacher has taught the curriculum model, the learner's understanding matches that target. Sometimes it does, but often it does not. And in my experience, that is true of even the most skilled class teachers. Now, the model I'm going to present today is underpinned by the perspective known as constructivism. This word is used in various ways in a range of fields, but the pedagogic notion of constructivism is much supported from work in the learning sciences and science education. The basic idea is that human learning is incremental, interpretive, and so iterative. By saying that learning is incremental, we mean that human learning tends to take place in small steps. Teaching needs to feed learners new ideas in manageable learning quanta that have to then be processed efficiently before the system can move on to process any further learning that builds on this. The amount of new material a person can take in during one class session or lecture is limited by their cognitive apparatus. By saying that learning is interpretive, we mean that what is already known, understood, thought, believed, has a critical role in making sense of new information. Generally, we understand something only if it makes sense in terms of prior experiences, and how we understand it is strongly influenced by that prior learning. This is why two politicians can look at the same economic data and have such totally different takes on what it means and what should be done about it. Perhaps it is why two keen observers can honestly disagree about the merits of a penalty claim in a football match. Prior learning here does not just mean schoolbook learning, but our wider learning from experience of the natural world and social interactions. We understand in terms of the interpretive resources we have already available, or at least that subset of those resources that are triggered as being relevant at any time. Given that learning is both incremental and interpretive, it follows that learning is accordingly iterative. Our understanding develops by a small step in a direction shaped by its starting point in our existing thinking, and that leads to a revised starting point to shape the next small step. Our developing thinking is highly contingent on what we already think. So, we might develop our model a little. It follows from what I've said so far that teaching needs to be carefully planned, taking into account the way people learn. The teacher has to have a good understanding of their subject matter, but that is not enough. Because learning is incremental, interpretive and iterative, the teacher has to be able to sequence teaching logically, break the material down into manageable learning quanta, and help students relate what is being presented to their existing conceptual structures. This means that teaching is informed by a mental model of the learner. The sequence and level and passing and phasing and mode of presentation will be effective to the extent that they engage the learner's interpretive resources in ways that support the development of the intended understanding. It seems then that the teaching presentation will imply some model of the learner's existing conceptual structure, the prior learning, the ways of thinking, the potential anchor points that can help interpret teaching. So we might say, again, that given what we know about how learning occurs, teaching implies a model in the teacher's head of what might happen in the learner's head when engaging with the teaching. That model may be implicit or explicit. Teaching is more likely to be successful if it is designed according to a well-informed model, so an explicit model is to be preferred. A teacher's model of the learner's cognitive system will be informed by their working with these present and past students, as well perhaps as from their teacher preparation and professional reading. If a major cause of teaching learning failures is an imperfect model, then the teacher who works with an explicit model is in a better position to reflect on their model and seek to modify it to make it more effective. The argument made here is that many teaching learning bugs are due to a mismatch between the teacher's mental models of how the learners will engage with teaching and how the learners actually process teaching given their actual existing cognitive structures. Given the complexity of any person's thinking, none of us can ever expect to develop an entirely accurate model of someone else's cognition. But if we recognise that the bugs are often mismatches and appreciate the kinds of mismatches that occur, then we are better placed to diagnose the bugs and address them. That is, a model of how mismatches might occur can be a useful tool for diagnosing teaching learning failures and treating them. We should not be too critical when teaching learning bugs occur, but we should seek to do something about them. The typology of learning impediments sets out the main classes of learning bug that teachers can look for. Classifying bugs may allow us to work with individual learners concerned, as well as informing modifications to teaching for future classes. Meaningful learning requires that, firstly, the learner has available interpretive resources that can help them make sense of a new teaching, and secondly, that they actually make a link. That is, that they perceive teaching as being related to their prior knowledge and understanding. This offers us some clues as to what can go wrong in teaching. Perhaps the student does not make the expected link. They do not perceive teaching as related to their prior knowledge. This can be for two main reasons. One is simply that the expected prior learning is not there. The prerequisite learning has not taken place. I recall a first-year undergraduate lecture where the professor of physical chemistry commented on one of his teaching points that we would remember this from second-year lectures. We clearly did not. However, it is also possible that the learner has indeed completed the expected prior learning and does have the relevant interpretive resources available, but does not perceive the teaching as linked to that prior learning, so does not bring it to mind, although it is needed to make sense of teaching. The learner may well be aware they do not understand, as teaching does not make much sense to them, and they may express this. Now that is perhaps the more obvious half of the story here, a failure to make expected links. Learning is basically associative. We associate the new with the established and assimilate it into our cognitive systems. If we find links that work for us, then we make sense of teaching, some sense, if not always the intended sense. There is then another potential source of system bugs, which is where a student does make a link with prior learning, but one that is not helpful in bringing about the understanding the teacher seeks. Again, there are two main classes of system bug here. Students commonly have alternative conceptions, and if they already misunderstand the topic area, they may interpret the new teaching as fitting in a distorted understanding of the science. The learner here seems to understand, the materials make sense to the learner, but later, perhaps in a test, it will transpire they've acquired a different understanding to that hoped for. It is also possible that the learner understands teaching in terms of some prior learning, some past experience, which is perceived as relevant, but which from a canonical point of view is unrelated. Here the prior learning may itself be quite correct from a scientific perspective, but when teaching is filtered through it, this leads to a new alternative conception. So, the basic model has four categories, grouped into two sets of types of learning impediments. It helps to have labels for the categories when we're thinking about, applying or talking about the different types. So some years ago I came up with a set of labels which perhaps make reasonable sense as labels. The first level of division was between null and substantive learning impediments. A null learning impediment meant the student failed to associate teaching with prior learning, that the teaching did not lead to the learner bringing to mind something that helped them make sense of their teaching. This could be because the expected prior learning had never happened, called a deficiency learning impediment, or because the relevance of prior learning was not appreciated, a so-called fragmentation learning impediment. The two main types of substantive learning impediments involve the learner making sense of teaching in a way that doesn't match that intended, either because the relevant prior learning includes alternative conceptions, and so the learning is distorted by being understood within a conceptual framework that does not match the science, or because the teaching is understood in the context of some other prior learning that seemed relevant to the learner, but which from the teacher's perspective was not pertinent. These are referred to in the model as grounded and associative learning impediments, respectively. Earlier, I used the metaphor of finding anchor points in prior learning for new teaching. And in those terms, we might suggest that these types of learning impediments are not finding anywhere to anchor new knowledge, a null impediment, either because the expected harbour had never been built, a deficiency impediment, or the harbour couldn't be located, fragmentation impediment, and anchoring the new knowledge somewhere but not where intended, substantive impediment, either in the right harbour but one that hasn't been built correctly according to the plans, grounded impediment, or in completely the wrong harbour, associative learning impediment. We might suggest Christopher Columbus suffered from an associative learning impediment when he arrived in the Bahamas and identified them as part of the East Indies. Another analogy that might be useful to catalyse your understanding of the model will be the binding of a metabolite in a cell with the relevant protein. What could go wrong? Perhaps the target protein is missing, so there is no substrate for the ligand to bind to. Or perhaps the protein is mutated in such a way that there is no functioning binding site for the ligand to attach to. Or perhaps the ligand diffuses to a different part of the cell and never comes into contact with the protein. Or perhaps the target protein has a mutation, and although the ligand is able to bind, it is strained by the abnormal conformation of the binding site. Or perhaps the ligand comes into contact with another protein of a matching binding site before it reaches the target protein. Each of these situations has some parallels with what can go wrong in teaching learning. Like all models, this model has limitations. A person's conceptual system, their range of different kinds of interpretive resources for making sense, will be complex and nuanced. Learning is a subtle process, in that it tends to be much more shaded than any simple model with distinct categories can offer. I do not claim that the teaching learning systems bugs always fit simply in one category, or even that we can always work out which category best describes a case. You will see that in some of my examples. My claim is that this is a useful thinking tool that helps us look at an instance of a student not understanding or misunderstanding to see if we can put matters right. A full diagnosis will often rely on talking to the learner, questioning them, and listening carefully to what they say, just as is often the case in medicine or in forensic investigations. So, if you prefer, you can think of this approach as being a learning detective rather than being a learning doctor. Given that health warning, here are some finer categories. Where students' existing thinking contains alternative conceptions, these can derive from several, or an interaction of several, sources. This includes direct intuition of the nature of the world based on experience of living in it. But it can also be due to folk knowledge that has social currency in everyday discourse, but which doesn't match the scientific models. Sadly, another source can be science teaching. The science teacher can teach things that are wrong or muddled. Even if none of us has ever done that, we likely know of examples of it happening. When learners make unhelpful associations, linking teaching to their prior learning but not the prior learning the teacher had in mind, this can be a completely creative process, making an idiosyncratic link that would not be apparent to most other people. However, sometimes there may be a linguistic basis. Words do not map uniquely onto the world. Sometimes one word has several meanings, or a word may sound very much like a different word. Many words adopted into use in science have been acquired from everyday language, where they may have a somewhat similar but often more vague referent. Another issue may relate to associations that arise from an over-literal interpretation of teaching. Teachers use models and analogies and metaphors and similes and anthropomorphisms and various other ploys to help make the unfamiliar familiar. That is, often when we need to teach some abstract idea that cannot be directly demonstrated, we either represent it imperfectly using some kind of model or diagram that can be directly shown to the learners, or we describe it in terms of something already familiar. This is a perfectly good, indeed sometimes essential strategy. However, our learners may not have the epistemological sophistication to appreciate that models and simulations and pictures are not realistic accounts of what is being represented, or that analogies and metaphors are only somewhat like the target concept and are not identical to it. I think there is a strong case for teaching children from very young that various kinds of models and representation and analogies have been used in science to generate ideas about how aspects of the world might be, to produce hypotheses to test, as well as to explain ideas to other scientists. That could avoid a lot of frustration for both teachers and learners. So, the learning doctor perspective is intended to demystify some of the reasons learning does not always occur when a teacher offers a clear and accurate presentation of some curriculum material. Now that we've considered the model, I'm going to talk about some examples of students' learning. One area of teaching that is well recognised as a challenge for many students is making sense of notions of atoms and ions and molecules, their nature, properties and interactions, and how these can be the basis of explanations of macroscopic phenomena. This is important across the sciences, but is especially critical in teaching chemistry, where a great deal of the subject concerns understanding how what could be observed at the bench can be explained in terms of models of what is imagined to be going on at the nanoscopic scale. Chemistry redescribes observable phenomena in terms of abstract concepts such as oxidation and sublimation, and then further redescribes them in terms of a narrative involving completely invisible conjectured entities such as ions and double bonds and distorted electron clouds that have unfamiliar properties. Electrons cannot be localized in space, and ions do not have distinct surfaces, and atoms are said to have completely different sizes in different contexts. And if that's not bad enough, sometimes particles can tunnel their way through barriers, like fantastical ghosts walking through doors. Learners who are told that the behaviour of substances they observe in the lab can be explained in terms of the molecules or ions of the substances often come to assume that this means that gold particles must be shiny, and wax particles must be soft, and copper particles conduct electricity, and ice particles melt readily, and so forth. Analysing this topic suggests there are a number of barriers to student understanding. Indeed, in terms of the typology of learning impediments, it can potentially tick most of the boxes. Probably the most reported alternative conceptions relate to the so-called naive physics or folk physics. People commonly assume that the force on an object must be in the direction it's travelling, so a moving object must be subject to a driving force, and moving objects will come to a stop by their own account without any resistive force being needed. An object tossed into the air, according to folk physics, has an upward force while it's moving upward, until gravity takes over, then it starts to move down. The naive physicist does not grasp the principle of inertia, and children asked to role-play dropping something from a plane onto a target will typically overshoot the target, assuming the payload will drop vertically. This can prove frustrating, though experience and practice can overcome the initial intuitions. Similar analyses could be made of other topics. For example, many learners struggle to understand natural selection, despite some biologists suggesting it's an obvious and simple notion. It is obvious and simple to those who've been working with the theory intensely for many years, less so for those first meeting the idea. The examples I am discussing have often arisen from my own teaching or research, so I'm not suggesting you would meet these specific problems in your own teaching, though of course you might. Some of these examples are discussed in more details in my publications or on my website. The following examples are meant as illustrative of the kind of analysis one can undertake to make sense of learners' thinking. This is quite a common alternative conception. In part, this seems to be a linguistic learning impediment, in that in the way in which the English language is generally used, we might expect a process that's been labelled as neutralisation to mean the production of something neutral, in the way that, for example, polymerisation leads to a polymer. However, if, for example, sodium hydroxide is reacted with ethanoic acid, it leads to a basic salt. This reasonable interpretation of language, that neutralisation leads to neutral products, is often made in teaching contexts where the reagents used to introduce neutralisation reactions are strong acids and strongly alkaline solutions, and where laboratory work may involve finding an endpoint by looking for a pH of 7. It may only be several years later that the notions of acid and base strength are introduced in more advanced courses, and neutralisation reactions which do not lead to neutral products first detailed. The pH of an aqueous solution will in part depend on the strength of the acid, but also on the concentration, and strictly also on the temperature. So any statement that a certain acid always has a particular pH is questionable. Yet I once found an experienced chemistry teacher who was convinced that the mineral acids always had a pH of 1. We actually met in the school lab with measuring cylinders at dawn, well, actually lunchtime, to test the idea with serial dilutions. Many years of teaching a course where pH measurement was limited to using indicator colours, and where students were taught the simplification that mineral acids would be found to have a pH of 1, had led to the teacher accepting the idea himself. I met students in my own college classes who, by the time hydrogen bonding was introduced in chemistry lessons, had already formed the notion that a hydrogen bond was a kind of covalent bond. This was in a curriculum context where school chemistry courses only discussed covalent ionic and to a lesser extent metallic bonding, and so hydrogen bonding was only explained later in more advanced, indeed post-compulsory classes. However, biology classes would be taught about how hydrogen bonding was involved in various processes relating to proteins and nucleic acids, without explaining further what hydrogen bonding was. Hydrogen bonding was clearly a bond to a hydrogen atom that was usually represented with a line from the hydrogen atomic centre to another atom in figures. So in the absence of any teaching on what a hydrogen bond was, a deficiency learning impediment, the students simply assumed that what was labelled this way was a type of covalent bond. One of the learning bugs I came across in my own teaching that rather surprised me concerned a student who was not sure how to relate the notion of multiple bonds to the ideas of covalent and ionic bonding. She suspected that there was a link, but was not sure. In my classes on general chemistry topics, I talked a lot about covalent and ionic bonds, whilst in the introductory organic chemistry class topics, another lecturer talked a lot about single and double bonds. Here, there was a kind of fragmentation learning impediment, as the student was not able to link up learning from the different parts of the course, as she had not appreciated that the bonds referred to in organic topics were covalent, as either the teacher had not made this explicit or this had been missed. I was very surprised in my work with my own students to find that they often thought that the Na plus ion was inherently more stable than the neutral atom, so the atom would spontaneously ionise itself, and indeed, even more worryingly, that the Na7 minus ion would also be more stable than a neutral atom. This led to some work which suggested this is very common amongst learners, and that students will often think that other ions with large charges will be stable, as long as they have outer electron shells that are full or have octets. Many students will even think that the excited chlorine atom, configuration 278, will be more stable than the ground state atom, 287, as the excited atom has an octet in the outer shell. This seems to be largely a pedagogic learning impediment, where teachers and/or textbooks have either explicitly stated, or at least strongly implied, that species with full shells and/or octets are more stable than those that have other electronic configurations. Of course, the octet rule is a genuine heuristic that can be useful in chemistry, but it only tells us that more often than not, ions in chemical systems such as lattices or solvated, and atomic centres in stable molecules will have octet and/or full shell arrangements. But learners will readily extrapolate from this that full shells and octets offer inherent stability in any context. As an analogy, consider the statement that spheres are strong structures. There is some truth in this, but it has to be understood in context. A sphere made of very thin glass, like a Christmas bauble, will readily break. A spherical submarine, subject to increase in depth, would eventually collapse if the pressure is sufficient. A marble dropped from a plane may not survive intact. It might seem that if learners have been taught a simple model of transformations of matter, that pure substances can exist as solid, liquid or gas with the associated transformations, melting, freezing, boiling, condensing, then once it acquired this idea and consolidated it through a range of examples, then it could be universally applied. But just because a learner knows that a liquid will freeze on sufficient cooling or boil on sufficient heating, this doesn't mean that they know this for all possible examples. Grounded learning impediments may interfere with the application of the principle in some circumstances. So, for example, if hot wax from a hydrocarbon-based candle is seen to solidify, the student may not consider this an example of freezing, as in everyday life world usage, freezing only occurs when it's very cold. Similarly, while a learner may have no trouble accepting that, like water, many other liquids will become gaseous if heated enough, they will intuitively know that this could not apply in the case of something like iron. For this particular pupil, iron was just not the kind of stuff that could become a vapour. I am not sure how widespread this particular alternative conception might be, but a 16-year-old just starting her advanced chemistry college course told me this. I might suggest a paraphrase that chemistry tells us that iron can become a gas, but it is hard to believe it. I recall interviewing a Year 7 pupil at a secondary school who told me that going to sleep, like eating food, could give us energy. When I asked him about this, he drew an analogy of recharging a battery, a creative association, though strictly a little misleading, as clearly sleeping may refresh us, but does not act as a net source of energy. Sophia was in Year 7 when she told me about the things she'd been learning in the topic of electricity, but she also told me she had done magnets. There was a sense of stream of consciousness here, as poor Sophia tried to suggest a convincing reason why the class had had a lesson on magnets when they were supposed to be studying electricity. She didn't seem to find a sensible option, and her best guess was simply that the teacher had given them a break from the topic. I suspect that the teacher would have seen things quite differently. But for the learner, magnets were solid objects that stick to things and had little to do with electricity. The idea that summer means we are closest to the sun has a clear difficulty, in that the northern summer coincides with the southern winter, and vice versa. Yet even young children will notice a pattern that when you're closer to sources of light, of heat, sound, perfume, the intensity is greater. If a student learns that the Earth's orbit is not a perfect circle, then it will be clear that our distance from the Sun must change at different points in the orbit. So, it is quite reasonable that this intuitively inferred general pattern would offer a feasible hypothesis for why it is warmer at some times of the year than others. Indeed, this is not an irrelevant factor, but simply not the most significant one in determining the seasons. Another idea that I was surprised to come across in my own teaching was the suggestion that an atomic nucleus with several positively charged protons will be held together by a force from the electrons. This idea is so wrong in many ways that it seems bizarre from a canonical perspective. This is certainly an example where, if prior learning from physics is being applied by the learner, they would not entertain the conception. When atomic structure is first introduced in basic chemistry, it's likely that the attraction between the positively charged nucleus and the electrons will be highlighted. But nuclear chemistry is a more advanced topic not taught at this level. So although the composition of nuclei, as usually being composed of several protons and neutrons, will be presented, the forces at work there, i.e. the strong nuclear force, will likely seem off-topic and an unnecessary complication. That is likely a sensible judgment, but it does leave an explanatory vacuum, as it should invite the obvious question: what holds the several positive protons in a typical nucleus together? In my experience, this is seldom raised by learners, which, if reflected more widely in other teachers' classes, may be another sign of the compartmentalisation of knowledge, the failure to think of the physics underpinning the chemistry, for example. If asked to suggest what holds a nucleus together, students are likely to build an explanation from fragments of what they have been taught. To a physics teacher, it should be obvious to learners that the nucleus is not being held together by the electrons, as Newton's third law suggests forces are mutual and symmetrical interactions. Even if some chemistry teachers do not keep such physics at the forefront of their minds, they will not expect their students to think that the negative electrons will be repelling positive protons to squeeze them together. Learners seem to fill the explanatory vacuum by associating the causal stability of the nucleus with the taught reason for the stability of the atom itself. Life for teachers would be more straightforward if all learners developed the same alternative conceptions. Other learners, when asked about the force holding the electrons in the atom, suggested this was gravitational. Although strictly there is such a force, it is minuscule compared with the electrical interaction. One likely source of this idea is a common notion, sometimes found in science books, that the atom is like a tiny solar system. Actually, at one time, this analogy was taken very seriously by some scientists, even leading to speculation that the little worlds in atomic systems could be populated and in turn made up of their own tiny atoms. Such ideas clearly did not survive the quantum model of the atom, with its orbitals replacing orbits. So, it seems likely this derives from overinterpreting a comparison as a realistic description. The atom is a tiny solar system. Perhaps sometimes this analogy is actually being taught by teachers without emphasising its limitations. Mandy, a Year 10 student, about 14 to 15 years of age, told me she got her energy from respiration. She also told me that plants also respire, but Here is a summary of what she told me about respiration in plants. Now, whilst this graphic helps me map out the comments she made in our conversation, I think it might be misleading, as it shows how certain ideas link up. But for a learner, this amount of material likely exceeded the capacity of her working memory. That is, she may well have thought these various things, but she was unlikely to be able to bring all of this to mind at once. I accessed fragments of her thinking by asking questions, and here I represent these as though they provide evidence that this all linked together for Mandy. I can add to this what she said about how she needed to respire as well. We can see that Mandy and other people need to respire all the time, whereas plants apparently mostly do their respiration at night. Now, I think one of the challenges here is that we can talk about respiration at the organism level or at the cellular level, and as teachers we likely shift back and forth. That is legitimate, as respiration for the organism is the aggregate of all that cellular respiration, but it must add to the learning challenge. Although Mandy talked about energy, the language she used reflected everyday discourse. It is often vague when compared to the specification of scientific language. Respiration made energy, glucose produced energy, and carbohydrates were energy. In a sense, the energy concept could be seen as the integrating idea needed to make sense of metabolism, and in particular of understanding how respiration and photosynthesis have a systematic relationship in plants. So, although my representation of Mandy's ideas into a network might suggest otherwise, Mandy felt that she did not know how the energy stored in food we eat, or in glucose used in plant respiration, got to be there. Mandy's conceptions of the two processes were balanced in terms of the substance involved, but not energy. That seems bizarre looking at the concept mapping here. Light is used in photosynthesis when it is absorbed by chlorophyll, so surely this is the source of the energy. But on reflection, I think Mandy meant it when she said that plants made energy by photosynthesis. One of her comments was that plants use the light to get the energy. It seems here that although she knew light was needed for photosynthesis and that it was absorbed in the chlorophyll, this did not imply to her that this energy became the energy somehow stored in the glucose produced in the process and later released in respiration. I think there are several things going on here, including a somewhat fuzzy energy concept and a suitably vague language for talking about it. But I think the critical issue is that Mandy didn't link the light needed for photosynthesis with the energy released from reacting glucose with oxygen in respiration. This link would have seemed so obvious to a science teacher that I doubt the issue would have come to light if Mandy hadn't volunteered to be interviewed. Indeed, I failed to fully appreciate this myself until I revisited the example when preparing the presentation for today. I could suggest a good many more examples, but I suspect you've seen enough to either dismiss this approach as not useful to you, or to think it may be something you could find useful in your work. But whichever option you take, I would like to remind you of my opening premise. Often, students fail to learn as we would wish because they're absent or distracted, or unable to hear clearly, or demotivated, or in some other way not in a fit state to learn. Yet it also seems to be the case that often learners come away from teaching when they could see and hear, and were making the effort to understand, but either couldn't make sense of teaching or misinterpreted it. We could put that down to poor teaching or stupid learners, but I think we all know better than that. We could claim that science is abstract and teaching it well is difficult. That would be true, but then I assume we've all volunteered to take up that challenge. We could quite justifiably claim that effective teaching will be possible if teachers are able to work in depth and over extended periods with individual learners. But that is not classroom teaching, where, in any case, student-student interaction can be very valuable. So we can either dismiss failures to learn as an inevitable outcome of an education system that works with students en masse, or we can envisage teaching learning as something which only works when the components are well tuned to each other and integrated into a system. From that perspective, system bugs may be inevitable, but they can also be analysed so they can be addressed. This particular model, then, is intended to address a real problem facing classroom teachers. Thank you.